Welcome, everyone. We are very happy to have Sebastian Mizera, who is going to tell us about the progress on high-energy string collisions. Yeah, please take it away.
All right. Well, first of all, thank you so much for the invitation to give this seminar, and it's a pleasure to be here remotely. So today I will be talking about a collection of work together with Lawrence Eberhard, as well as Pinaki Banerjee and Bacchianti. So the talk will be focusing on string theory. And to me, string theory is exciting because it gives us a rare window on the physics of quantum gravity. And in this talk, I will be using a kind of a particle physicist approach, and I will consider the following thought experiment. So I'm going to take two strings, and I'm going to smash them together at high energies. And as we know, what's going to happen as the result of this collision, there's going to be a number of other strings flying out. And you would imagine that by trying to understand various different angles and energies at which they come out, that would give you, in principle, handle on the physics of interactions in this regime somewhere here at small length scales. So before going into details, let me kind of introduce a couple of parameters that govern these kind of string interactions. The most basic one is the string scale that I will be calling L sub s. And it's also identified with the parameter or square root of the parameter called alpha prime that is often used in this context. So when I talk about high energy collisions, what I mean is that the center of mass energy, or square root of s, has to be much, much larger than 1 in the units of the string scale. Okay, so this is going to be the setup. And what we're going to do in this talk, I decided to divide it into 4 parts. And in the first one, I will tell you some kind of motivational aspects, why we're doing what we're doing. And this will, I will try to explain to you the so-called phase diagram of gravitational scattering. And I will explain the regime in which we're trying to study. And then in the second part of this talk, I will move on to string perturbation theory, and I will tell you some of the details of how we formulate string perturbation theory in Lorentzian spacetimes. And this will lead to a small puzzle. And the rest of the talk will be about the resolution of this puzzle. And that resolution will have to do with formulating string theory on Lorentzian worldsheets, and it will result in concrete results. And those concrete results are kind of flashed here. This is a sneak peek of what's going to happen, what we're going to try to understand towards the end of this talk. We're going to understand 2 numerical plots of scattering amplitudes plotted at high energy at fixed scattering angle and at fixed momentum transfer. Okay, but before going there, let me start with the motivational part. So the first question that I wanted to ask is what can be in principle measured in a theory of quantum gravity? So the simplest object that we can try to compute in such a theory would be an elastic amplitude, say of massless excitations in your theory. So this would be just the 2-to-2 exclusive S matrix element. Another object, which is much closer to the kind of the picture that I showed in the first slide, is this. 2 things fly in, but there's a number of other kind of excitation modes flying out, and this would be an inelastic contribution to the amplitude. And eventually, what you're actually interested in computing are these more complicated observables, the cross sections or inclusive cross sections, in which you sum and integrate over the phase space of kind of undetected states, and then you're trying to understand the energy spectra of some other states in your theory. Okay, so in principle, all of these are very interesting, and I think basically, if you go to the right of this plot, the less and less is being understood. So most of the talk will be focusing on this. This elastic contribution, so 2-to-2 amplitude, with the view of potential applications to these more complicated cross sections and so on. So since we're studying the elastic amplitude, let me first explain the kinematics that we deal with. Okay, so this is a spatial plot. So we have particles with momentum P1 and P2 that come in, and there's some particles with momentum P3 and P4 that fly out. So this is traditionally parameterized in momentum space by two kinematic invariants or Mandelstam invariants, S and T. So let me remind you that S is the one that is equal to the sum of the momentum of the incoming momenta P1 and P2 all squared. So this is the center of mass energy squared, and it's a positive quantity. And on the other hand, we also have the momentum transfer, T, which is the momentum transferred between the blue and red particles in here. So this quantity, which is a purely space-like quantity. In fact, people often would parameterize it in terms of the space-like vector Q. So T in that notation has to be a negative parameter. Just to explain this connection with the phase diagram of gravitational scattering, just for the next slide only, I will briefly switch to the parameterizing everything in terms of S and B, where B is the impact parameter. So this quantity in here, and you can think of the impact parameter as being canonically dual or a Fourier transform of the momentum transfer. So roughly speaking, B is equal to 1 over Q. Okay. So this is enough background to understand the following plot. So I'm going to review it in a single slide, even though there's been kind of an enormous amount of work that went into trying to understand these kind of aspects of gravitational scattering that dates back to the work of Amati, Cefaloni, and Veneziano, started back in the 80s and continued until this day. So actually, if you would like to learn more about this, I highly recommend reading this review that appeared last year. Okay, so what we're going to look at is we're going to look at everything as being parameterized in terms of S, or square root of S in these string units, and B, the impact parameter, also in the string units. So what we want to do is essentially we want to study the high energy behavior on this plot. So the high energy behavior is somewhere far away for large S and large B. However, it turns out that you can approach this limit in different ways. So the simplest limit is in which you take the energy to be large, but the impact parameter parametrically even larger. So this would be, you can think of it as scattering of objects interacting through gravitational interactions at very large impact parameter. So this is known as the Born regime, and you can think of it as two heavy lines that only exchange a single graviton between them. So this gives rise to the Newtonian potential. Then you can ask what happens as you start decreasing the impact parameter. So from the Born regime, you explore the so-called iconal approximation. So iconal is the one in which you don't exchange just one graviton, but you exchange an infinite number of gravitons, cross-ladder diagrams. And then as you keep decreasing the impact parameter, you find the contributions from tidal excitations, and then contributions from the gravitational waves being emitted from this process. And eventually, at parametrically small impact parameters, so this is roughly kind of a head-on collision of two objects, we suspect that this is dominated by black hole production. Okay, so all of this has been asymptotically at large energies. And now what we wanted to answer, what happens if we increase it? And you increase it so much that in the string units, the impact parameter is below the string scale, and likewise the energy is below some string scale as well. It turns out that actually the transition between the stringy and the black hole effects happens roughly at this order, where GS here is the string coupling. Okay, so this is the regime in which you would like to explore things in using string theory. And what we're going to do in this talk is in fact try to kind of push this boundary of starting with string theory in perturbation theory, so at weak coupling. And by studying the high energy behavior of that, we'll try to approach this boundary in which stringy effects match onto the black hole effects. Okay. So here I've illustrated this with these two arrows, and that's because there's actually two different ways that we can talk about the high energy limit.
Sorry, Sebastian, I have a question about the...
Yes.
So you're just scattering gravitons on gravitons, right? Or is this...
Correct. Yes, correct.
For example, so what does tidal excitation mean? I thought tidal would mean some extended object.
Yeah, exactly. So the type, so this plot actually would apply to, well, at high energy, you would imagine that you can approximate all the particles as being roughly massless, but then you can add the structure to the particles. So this would, in the wordline language, for example, would refer to insertions of higher derivative operators on the wordline. So this is probing kind of the going beyond the point particle approximation of these objects.
Okay, so this is like some form factor might change between that object and the graviton or something, or?
Yeah, that's a good way of thinking about it.
Okay, thanks.
All right. So as I said, I will not mention this plot beyond the motivational part, but what I wanted to mention is that these two ways of approaching the high energy limit, and we'll focus exclusively on perturbation theory in this talk. So this means is that the G-string, so the coupling will be fixed and small. Okay, so the first limit that you can do is you can take S and T to be simultaneously large in the units of alpha prime, but in such a way that the scattering angle, so the cos of the scattering angle is given by this formula, remains fixed. Okay, so ST large, but the ratio of S and T being fixed, and that corresponds to the fixed scattering angle, which is drawn here. And another limit that you can explore is the so-called fixed momentum transfer, which is the one in which you take the energy to be large, but then the momentum transfer T to be fixed. Okay, so we'll study both in the later part of this talk. So before doing so, I wanted to tell you or remind you a little bit about string perturbation theory in general. Okay, so for concreteness, for the purposes of this talk, I will focus on gluon scattering in type 1 superstring in the critical dimension, which is 10. Even though we know how to generalize a large part of this story to, say, type 2, so closed string scattering, also in critical dimension, I will just use this as a simplification for this talk. Okay. So what we study here is the planar contribution to the scattering amplitude. So that is depending on, as promised, on S and T. And then everything is given in terms of perturbation theory, which contains the tree-level diagram. This is the first one. This is also known as the disk contribution. So pretty much everything is understood about the disk contribution, and we'll discuss it on the next slide. But what will be the focus of this talk is these two first quantum corrections. So both of them in the quantum field theory language would be called one-loop contributions. So the one-loop or genus 1. And there's actually two topologies that you need to consider in the planar sector. And this is the annulus and the Mobius strip. And as I indicated with these question marks, there's actually a number of open questions that relate to the formulation of string perturbation theory on these topologies. Okay, so in this talk, I will be taking what I call the give me the numbers approach to scattering amplitudes, which states the following. All I want is to be able to plug some numbers. So let's say S and T, some positive and negative numbers. And I want the answer to as many digits as possible. Okay, so this is a good test as to whether you understand what the computation that you're doing. If you can reliably extract the numbers to high accuracy, this means that essentially you can study whatever you want in the theory. You can plot the amplitude, you can study it in different limits, and so on and so on. So as we'll discover, this can be actually achieved at tree level, but at one loop, at higher loops, turns out to be a very difficult task. So let me review what happens at tree level. So tree level was this kind of worldsheet, and this is known as the Veneziano amplitude, which is given by this famous formula. So let me explain the notation a little bit here. So first of all, we have this T8 up front. So this is called the T8 tensor, and that includes all the polarization dependence of our scattering. So it includes all the contractions between polarization vectors epsilon and the momentum vectors P. This is kind of a universal factor that is always there up front. So when I will be plotting things, I will just set it to 1 for this purpose. So all the stringiness of the formula is actually contained in this collection of gamma functions that depend on S, T, as well as alpha prime, which is physically it corresponds to the inverse string tension. And for the purposes of the plots, I will be also working in the units in which alpha prime is equal to 1. Okay, so this is a beautiful formula, as I'm sure many people in the audience appreciate. You can read off the spectrum of string theory from the resonance from the poles in this formula. You can look at the low energy behavior in which you recover the Yang-Mills theory. You can look at the high energy. You can look at the Reggie, and so on and so on. But for the purposes of this talk, the question is, can we get the numbers for whatever kinematics I plug in? So what I've plotted here, the answer in this case is yes. And what I've plotted in here is the planar, this is the Veneziano amplitude as a function of S and T, where I've plugged in T, the specific value, which corresponds to fixing the scattering angle to 60 degrees scattering. And then the only parameter that we are going to increase is the energy S in the units of alpha prime. Okay, and as you can notice, I've also divided and multiplied by these factors of sine. And these are simply to make the plot look nicer. So there's an infinite number of resonances at the integers. So the sine is simply to kill the poles so that you get a smooth curve. And likewise, this one here is to remove the zeros. Okay, so what are some of the properties of this function here? Well, first of all, I've plotted everything on a logarithmic scale. And you see that asymptotically for large S, this plot approaches a constant, but we're on a log scale. So that means that in fact, it's exponentially suppressed. And if you work out what the exponential suppression should be, it's actually equal to the suppression by the on-shell tree-level action, which in this case at the 60 degrees is some constant times S. Okay, so that's why we get the exponential decay. Okay, so that was very easy, mostly as a review. And what we're going to do next is we're going to look at basically all the same structure, but at one loop. Okay, so as I mentioned, at one loop, we have the planar annulus and the Mobius strip contributions, which are illustrated here. So what we see here is by now a textbook result. This is a computation first done by Green and Schwartz, who've computed the correlation function of vertex operators on the annulus. And they arrived, after all these computations, they arrived at this simple looking answer. Okay, so these collection of Jacobi theta functions, they depend on the positions of the punctures Z, as well as the modular parameter tau. Okay, so in case you haven't seen this before, let me just explain it quickly. What you do is you identify the worldsheet with a rectangle in here, in which that side and that side of the rectangle are identified. So that's the annulus. And then what you do is you insert punctures at the bottom boundary. In fact, by rotational invariance, you can fix position of one of the punctures, say Z4 to be 1. And then you have to integrate over positions of the remaining punctures. And you also have to integrate over all geometries of the annulus, which is this complex parameter tau. Okay, so in fact, this is what you see here. We're doing just a path integral over all geometries. So that means that I integrate over the planar ordering of the vertex operators on the boundary, and I also integrate over the modular parameter. Okay, so the modular parameter goes from 0 to I infinity. So 0 corresponds on this, as you can tell on this picture, corresponds to very thin annuli. Okay, so this is roughly the limit in which you expect to see Feynman diagrams arising. And on the other hand, tau goes to I infinity is a very thick annulus. Okay, and then as before, all the polarization dependence goes up front, just like in the case of the Veneziano amplitudes. And it turns out you can actually repeat the same analysis for the Mobius strip contribution. So this was the annulus. The Mobius strip is very similar. The only difference is that the integrand is the same. The only difference is that tau, you have to integrate between 1/2 and 1/2 plus I infinity instead of 0 and I infinity. And the other difference is that you get a suppression by a factor of 32 over n, where n is the related to the is the rank of the SON gauge group. Okay, so this is great. So what this means is that there's a very explicit formula for both contributions, and now we want to extract the numbers. So what that means is that in principle, we should be able to do the following exercise. We should be able to just copy paste the expression from the previous slide, plug in some numerical values for the S and T, and just integrate this. But those of you who have done this exercise in the past would know that this actually results in a horrible divergence. Okay, so if you just naively try to integrate it in Mathematica, you would find infinity. So the bottom line is that if you just copy and paste a textbook expression from a string perturbation theory, it cannot be actually used in practice if you just wanted to integrate it. So what I wanted to convince you of on the next slide is that this is not a numerical issue. It's not a computational issue. It's a very conceptual issue that will have to be solved. Okay, so it's not a numerical problem. And the one way to diagnose where the issue came from is that if you study the formula on the previous slide, you would see that, in fact, the integrand that I showed you was completely real. Okay? And then on top of that, we integrate over the complex modular parameter, but also there was an I up front, so that contribution is real. So as we've seen on the previous slide, it in fact integrates to infinity, it just diverges, but it's in fact even worse. It's a real quantity. Okay, so this is a very bad sign because the fact that the reality condition means that this result cannot be possibly consistent with space-time unitarity. So space-time unitarity would tell you that SS dagger is equal to 1. This is the statement that all probabilities add up to 1. So this would imply that the S or the S matrix has to have a phase. So it has to have a real and imaginary part. So the imaginary part is important because the imaginary part is related to the particle production. Okay. So let me give you an analogy for this problem. At the level of Feynman diagrams, this is exactly the same problem as if you try to integrate over some propagator, but you forgot about the I epsilon. Okay, so of course we get the divergence because you just L squared can hit the pole, but also there's no I epsilon, so that means that it's a real divergence. So it's exactly the same problem. Okay, so what this tells you straight away is that in principle, you need to, well, in quantum field theory, this would be resolved by the I epsilon prescription, Feynman I epsilon prescription. So what you're looking for in string theory is some prescription that is telling us about the I epsilon or Lorentzian continuation of our result. In fact, let me distinguish between two separate challenges that we are facing. There's a conceptual and a computational challenge. So the first one is the conceptual challenge, which is asking what is the integration contour on the moduli space of genus G Riemann surfaces with punctures. So equivalently, you can think of it as a question about the compactification of this moduli space if you're more mathematically oriented. And in fact, you could have guessed that maybe something like the Lee-Mumford compactification, which is a popular topic in mathematics, would resolve this issue, but in fact, it doesn't. So the Lee-Mumford doesn't talk about anything a lot this I epsilon prescription. So what we're looking for instead is looking for the role of the Feynman I epsilon in string theory. So that question actually turns out to be fully understood at tree level. So one loop, the one that we're studying now, is the first interesting case in which that until recently was an open question. And let me mention that this is not a problem that I'm just inventing here. It has been studied for a long time by a number of people who have came up with different proposals for how to address this problem. Okay, so I've learned about this from a paper of Edward Witten from around 10 years ago or so, who explained physically how to implement such a prescription. So from now on, I will call it the Witten-Iepson prescription.
Sorry,
Okay.
Sebastian, about this point about the Deligne-Mumford compactification. I thought the string field theory approaches sort of work with that compactification because you go to some boundary of moduli space where you have a degenerate Riemann surface, and then you just write a different Feynman diagram with an internal propagator. So, I mean, is your statement just in the context of a particular formalism of string theory, or
Yeah, that's right. So this is a problem specifically in the worldsheet approach. I was going to comment a little bit on string perturbation theory. So there are actually, it turns out, string perturbation theory. There actually the problem of Iepson is also not exactly trivial, but very recently has been resolved by Reggie Pius and Ashok Sen and collaborators. So in a sense, this conceptual issue there, as far as I understand, has been resolved.
Okay, so basically, Deligne-Mumford can be used if you use the string field theory approach, right? Is that correct, or?
As far as yes, that, but together with some prescription of how to integrate over the non-local vertices in the Lopinton space. So there, you need to do some additional work that has been done.
I mean, you have to, on top of Deligne-Mumford, you have to specify extra epsilon in string field theory. Yeah. Yeah, exactly. Yeah.
Yeah, I agree. Then let me mention, this was a conceptual issue. There's also the computational issue. So even if you knew the integration contour, there's a kind of an open question in general about how to integrate over this contour. So one thing that I wanted to mention, the difficulty with actually using these contours in practice is the fact that if you look at the integrand, it tends to oscillate very fast. So it's kind of akin to a sign problem that we often encounter, and this typically makes explicit computations very challenging. So the resolution in that I will present in this talk is to, instead of trying to integrate these functions directly, I will convert these integrals into an infinite sum representation. And this will allow us to avoid these kind of problems. And I think there's also an open question here in string field theory, in which, as we discussed a second ago, I believe that the conceptual issues have been resolved. So what remains is the computational issue, and I think it would be very exciting if we could also make these explicit computations or reproduce some of the results that I will be talking about also using string field theory. Okay, so I mentioned some of the puzzles, and then next I will talk about the resolution of these puzzles, and I will also with the ultimate goal of explaining some plots of string amplitudes. Okay, so before diving in, let me try to play a little game, and let me try to ask if we could have predicted how the planar contribution to the one-up contribution to the planar amplitude could look like without doing any concrete computations. Okay, so let me just kind of review what we expect this to look like. So first of all, if we look at 1, 2, scattering 2, 3, 4, we know from unitarity, from cutting rules, that there's going to be a particle production associated to putting the intermediate states on shell. So the intermediate states could be here and here. And as we know in string theory, the masses m of these states are quantized such that they're square roots of an integer n1 and n2 in the units of alpha prime. Okay, actually doing this, you could have thought about doing this computation directly, just from using unitarity methods. But here, one of the aspects of string theory, which is the exponential degeneracy at the given mass level. So if you fix mass level, and you count the number of states at the given mass level, it turns out to grow exponentially, which is a famous fact in string theory. So this actually means that if you wanted to talk about these unitarity cuts, you would have to take into account these infinite number of states. Exponential number of states. But more practically, what this analysis here tells you is that there's supposed to be a discontinuity whenever the energy S is enough to be able to produce these two states, M1 with mass M1 and M2. Okay, so whenever we cross a threshold looking like this, then we should have a discontinuity in our amplitude. And let me remind you, if you translate it into the mass levels, N1 and N2, that means that that the answer is going to be some crazy function that is going to jump whenever S crosses this threshold of a square root of an integer plus square root of an integer all squared. Okay, so it's kind of difficult to imagine a closed form formula for such a function with this property. And I believe this is essentially the reason why this formula for the one-loop amplitude is not known in the literature. Okay, but essentially what this tells us is that if we try to reproduce the plot that we've seen previously at tree level, but now at one loop, so we've computed this quantity in here, the way it has to look like is going to be as follows. So we're going to have the amplitude. Once again, I'm going to fix t to this value, which corresponds to scattering at 60 degrees. And I've indicated here with these dashed lines, these are the values of S for which there's going to be a discontinuity. So for example, this dashed line here corresponds to S equal to square root of 3 plus square root of 5 all squared.
Hello, can I ask a question?
Please.
Is it possible to avoid this problem by going to complex S-plane? Go off the real axis a bit?
Yeah, so depends on, so yes, that's right. So there we would not have thresholds, although the analytic structure will still have to see the square roots and logarithms opening up. We just see them kind of smoothed out a little bit in the complex plane. Unless you mean going directly up in the S-plane.
No, not directly up, but work at some generic point in the upper half S-plane.
Yeah, so
or maybe just go parallel to the real axis.
Yeah, I will mention this a little bit. So what I wanted to study in this talk is specifically the real axis, but I will mention towards the end of the talk how we think about going slightly into the upper half plane.
Yeah, the other question is that at tree level also this problem exists because of the poles, but you avoided it by multiplying by that function, right? Ratios of signs. So is there something similar that can be done in this case?
Yes, so I'm going to multiply out by so this is going to be actually the next, I'm going to explain it in 3 slides in which I'm going to multiply by a similar factor to get rid of the double poles, double poles.
I see, okay, thank you.
Okay. So let me mention the next piece of information that we, in principle, now can predict about the plot of the amplitude, which is about its asymptotics. So one way that
are you going to show a plot on the previous slide, or was that just?
For now, it's empty, and I'm going to add more information on this plot, and ultimately, we're going to see the final result.
Thanks.
Sorry, I should have made it clear. Okay. So in principle, we could study asymptotics and the fixed angle, which from the worldsheet perspective is dominated by saddle points. Actually, if you do this analysis carefully, then you would discover that there's an infinite number of saddle points. So each of them would contribute some e to the minus s, where s is the real part of the action. But in principle, it can come with some coefficients. Okay, so actually the working hypothesis in this business has been that, which is due to Gross, Mende, and Manius, is that there's one symmetric saddle that is dominant. Moreover, they worked out, or they predicted, that the saddle has its real part of the action is the same as at tree level. Okay, so the prediction would be that the amplitude is exponentially suppressed, and it's exponentially suppressed in the same way as at tree level for open strings. Actually, some speculations how this resounds at all genus, but I will not mention this. Okay, but let me emphasize that we actually don't know exactly which saddles dominate or don't dominate, because at this stage we have not actually even talked about what is the correct choice of the integration contour. The choice of the integration contour is going to, this is the Stokes phenomenon, is going to select which saddles are actually the relevant ones. Okay, and in fact, we're going to see that this story with a single saddle being the dominant one cannot be entirely correct, as we will see from the numerical data. But nevertheless, what we can put on the new piece of information that we can put on this plot is the exponential suppression that is the same as I mentioned at tree level. So that means that if we manage to plot the amplitude, it would have to roughly follow these dashed lines in here. Okay. And in fact, we even know slightly more information. So this pertains to the question of Ashok.
Just a minute. You have two dashed lines. What's the other one? Or
this just indicates the slope, and I've not committed to the intercept. Okay. So the additional information that we have is also from these kind of degenerations of the worldsheet. So we can pinch the worldsheet in these places, so here and here, such that, roughly speaking, it corresponds to this bubble Feynman diagram. So you can think of this as this place and this place as creating a propagator here and here. So what this tells us straight away is that if we actually looked at the worldsheet computation and tried to compute it, you would have double poles corresponding to an integer mass level and the integer mass level exchange here and here. And in fact, we know slightly more, and this is precisely with the analogy with the 1pi resummation in quantum field theory. We know that this basically dresses the propagator. So there's some sigma that depends on the mass level and on t. And the sigma physically corresponds to the average mass shift, its real part. And the imaginary part corresponds to the average decay width at a given level. So luckily for us, this has been computed in many papers in the past, in various different theories and so on. So this gives us some additional data that we can in principle put on the plot. So what I'm going to do here is I'm going to now put the information about the imaginary part in blue and the real part in orange, and I'm going to multiply it by sine pi s all squared in such a way that the integer values, basically, they give me the decay widths and the mass shifts that I mentioned on the previous slide. Okay, so if you put the data, what we get is we get a new data point at every integer. So if you collect all this information from the literature, so they're here. And one thing that I wanted to emphasize is that already from here, it's clear that the imaginary part in blue is on the logarithmic plot. So you can see by the offset here is that it's dominant by a couple of orders of magnitude. So the imaginary part dominates. So this is very funny because at the beginning I mentioned that if you look at the formula, it's purely real, and then you need to add the I epsilon. And you might have thought that the I epsilon is some small subtlety that we just need to fix. But it actually turns out that it's not a subtlety, it's actually an order one, is the leading effect. So it's going to be very important to be able to understand the origin of the imaginary part. Okay, so this is pretty much how much we can get out of the results in the literature and trying to collect some physical intuition about the result. And then what we're going to do next is I'm going to prescribe the contour that I'm going to work with, and then we'll see how it fits on this plot, how the result fits on this plot. Okay, so let me go back to the integration contour. So remember in the tau plane, the modular parameter plane, I have to integrate between 0 and I infinity to get the annulus contribution. And the bottom, the origin, the neighborhood of the origin corresponded to the thin annulus. So this is the roughly the Feynman diagram limit. And this is precisely where you need the correct I epsilon issue, I epsilon prescription. And on the other end of the integration contour, so tau goes to infinity, we get the thick annulus. And this, in fact, corresponds to the soft dilatant divergence. So it corresponds to what happens if this inner boundary of the annulus shrinks to a point. Okay, so long story short, let me just tell you what is the new integration contour, which we claim implements the Witten I epsilon prescription. So the new integration contour is going to be modified in the neighborhood of the origin, and it's going to approach the origin, but from the right-hand side at the 0
Sorry,
angle.
Sebastian, maybe I should have asked this before. So tau is the close string time in your conventions?
Yeah, that's correct. That's correct.
Okay.
So
Tau is the close string time.
Yeah, that's correct. So yeah, so maybe I should have said from this perspective, you can understand the moduli space of the open string would be some middle dimensional cycle, which is this red curve in here, in the closed string moduli space. It actually requires some extra curve. It's really the complexification of the closed string moduli space, but I didn't want to get into details. The bottom line is that that we need to, the compactification from this perspective, it amounts to a change of the integration contour. The change is as follows. So this comes from matching with the quantum field theory, the limit as tau goes to 0, is matching the Feynman I epsilon with in this limit. Okay, so this is what I said here. The reason why the direction of the approach at this point matters is that there's actually an essential singularity at the origin. In fact, there's an essential singularity at every single rational point of the real axis in here. So whenever you approach at essential singularity, the path of the approach gives you a different result. So that's why what I'm drawing here is not a contour deformation of the previous result. It's a new contour. In fact, what you can put on this
I didn't quite get why you have to put this semicircle here. Could you just explain one more time?
Yeah, absolutely. So I would not have time to explain it in full detail, but roughly speaking, you can study how the limit as tau goes to 0. This is the limit in which the worldsheet degenerates into a word line. And then on the word line, we know how to put the I epsilon prescription. So this contour is chosen precisely in such a way that in the limit as tau goes to 0, then this result matches with the I epsilon prescription.
So that controls the contour close to 0, but how do you fix it away from it? Like this 2 pi I over t star, is that arbitrary or?
Yeah, that's completely arbitrary. So that's a great question. So there's a lot of problems at the real axis, but in fact, the integrand is completely holomorphic in the upper plane. So the only thing that matters is how you connect it to, in which way you connect it to 0, but the precise shape of the contour upstairs doesn't really matter.
And the semicircle is tangent to the real axis or it's at some angle?
It's tangent. That's
tangent. Okay, thanks.
So you can repeat the same analysis for the Mobius strip. And let me just mention that the result is the same. What you have to do is you have to attach this hook in here, likewise in here. Okay, so let me mention this was the modification close to the origin. I also mentioned that there's a problem at infinity. However, the resolution of this problem has been known for a long time due to Fischler, Susskind, and Polchinski. And to understand it, we have to remember that if you remember from one of the previous slides, there was a suppression of a factor of 32 over n. There was also a minus sign. So the minus sign corresponds to reversing the contour for the Mobius strip, which goes down as opposed to up. And then both of these contributions are divergent, so they meet at I infinity, and they meet with the opposite orientations. Both of them are divergent, and the divergences cancels if and only if the n is equal to 32. So this is how we see the famous SO32 gauge group in type 1. Okay, so what I'm going to do on the next slide is I'm going to compute as a training example, not the full amplitude, but instead its imaginary part. So the imaginary part turns out to be much easier. And the reason for that is that the imaginary part is basically the difference between the plus I epsilon prescription and the minus I epsilon prescription. So the plus I epsilon gives you these hooks, drawn here, and the minus I epsilon just reverses the hooks to the other side. So the difference between these two prescriptions are basically these two circles. Okay, so the claim is that these two circles compute you the imaginary part of the one loop amplitude. And let me kind of reiterate what we already discussed a second ago. The only thing that matters is the approach of these circles at the 0 and 1/2. But the way that they are drawn in the upper half plane is completely arbitrary. In fact, what you can do is you can shrink them to be arbitrarily small, but non-zero. So this is actually why this is such a powerful method. And the reason for that is that you can basically shrink them to be arbitrarily small. So that means that you can then expand the integrand around these 2 points, 0 and 1/2. And then you can basically take the leading orders in this expansion and get the exact result. This is actually related to the math topic called the tropical analysis, and this is how you see this infinite number of discontinuities that I mentioned before. Okay, so basically you can implement all that on the computer, and the result of all these computations is the following plot. So this is the plot that we've seen before. The only thing that I've added on this is the result for the imaginary part. And the first thing that you see here in blue is that it passes through all these points and the integers that we've seen before. So it matches with the computations of the widths. Okay, the spikes look slightly funny, but this is only because we're on the logarithmic scale. So the spikes just corresponds to the zeros of the imaginary parts. And as promised, we see that on average, there's an exponential decay of the amplitude. Okay, so it follows these dashed lines. But we see that the exponential decay is actually not exact. There's some oscillations on top of it. So that means that if you really wanted to reproduce this result from a saddle point analysis, it probably means that there's multiple saddles with the same real parts, but different imaginary parts. And this is what gives you this competition of the phases, and it gives you these oscillations. And that's in fact something that we're trying to understand now independently, analytically.
But you've also multiplied by the sine squared, right? Which is oscillating itself.
That's right. But if you look at the period, it's actually, the period is not related to these oscillations.
By the way, just a note on the time, we can go on for 40 more minutes. So if you have time, then we don't need to rush too much. Yeah.
All right. Yeah. Okay. Excellent. I was just going to ask. Thank you.
Just one question. So are the zeros at random points, or they are because of the sine square pi s multiplication?
The zeros, we did not manage to recognize a pattern as far as I remember. They look close to integers, but not quite. So they're not because of this.
I see. Okay, thank you. Yeah, but sometimes if the double pole is absent for some reason, you could get zeros, right?
Yeah, I think one reason to see that it's not the double pole issue is that these integers that are drawn here. So these are the integers. So that means that there's a double pole with a non-zero residue, and but the zero happens very close to it, but not quite. It's a bit funny. I don't know how to understand it.
Okay, thank you.
And another thing that let me mention here is that this formula, as I promised, it was supposed to have a discontinuity at every dashed line here. And in fact, it does, except the thresholds open up very, very slowly. So the discontinuity is very, very small, and it's actually difficult to see from the numerics. But we can show analytically that this is actually discontinuous. Okay, so this was the imaginary part. Let me move on to also discussing the real part or the full answer. Okay, so this is just the plot.
Just to understand the last comment, you're saying this blue curve really has some jumps at all the dots that are kind of small and
yes,
you're not seeing them on this plot, but they're there.
Yeah, so the jumps are of the type of, say, well, in the paper, we give all the exponents, but roughly speaking, they're like square root of s minus some number. So that means that that's why it opens up very slowly. Basically, it's the value is continuous, but
yes, some square root thing at the threshold, you're saying.
Yeah, exactly. So we actually worked out for all these thresholds. It depends actually a little bit on the number theory of these square root of n plus square root of n2 all squared, and they open up. They all open up at different rates, but we have control over this analytically.
Okay, thanks.
And I think I will show one more plot in which these discontinuities would be visible slightly better. Okay, so let me come back to the contour that we've drawn before. Let me actually emphasize one thing that we already stressed is that the integrand is holomorphic in the upper half plane. So this means that you can freely actually deform the contour in the upper half plane as long as you don't modify its endpoints. Okay, so in principle, we can actually divide it into pieces, into two pieces that I called capital gamma and lowercase gamma. So one goes to I infinity, and the other one goes to the lower parts of the upper plane. So it turns out that this contribution from lowercase gamma can be actually evaluated analytically. So it's we've seen that there's a cancellation of divergent terms. So underneath that, the cancellation, there's actually a finite term. This finite term actually turns out to be an alpha prime derivative of the Veneziano amplitude. So we'll come back to this point. It will turn out to be very important later on. But for the time being, I'm going to discuss this difficult part of the contour, which is this capital gamma downstairs. Okay, so since I have some additional time, let me explain the fun number theory behind how to understand the deformation of this contour gamma. But in order to understand this, let me make a small detour into some little definitions from number theory. So let me introduce
before we go on.
Yes.
The imaginary part plot that you showed is the sum of the annulus and Mobius strip, or
yes, that's correct.
You've added the two.
Yeah.
But separately, they're also finite and computable, or do you have to add
they're separately finite and computable. Actually, it's a great question. I believe that if I remember correctly, annulus is leading to the Mobius strip. So, yeah.
Annulus gives the larger contribution.
Exactly. But they're both, the major parts are finite, the real parts diverge. Yeah, okay. So then I was going to talk about the Fourier sequence. So let's call it F sub Q, which is going to list all irreducible fractions between 0 and 1, such that the denominator of that fraction is bounded by Q. Okay, so for example, F1, we're going to list two fractions, well, 0 and 1 written in this way, where the denominators are bounded by 1. And then F2, we're going to add 1/2, and then at 3, we're going to add 2 more fractions, and so on, and so on, and so on. So in the limit as q goes to infinity, we're actually going to enumerate every single irreducible fraction between 0 and 1. Okay, so now on top of that, what I'm going to introduce is I'm going to introduce a fourth circle. So for every fraction, p over q, I'm going to draw a circle that touches the real axis in the tau plane, the corresponding rational point with a specific radius. And then it turns out it's very fun to draw. If you actually draw these circles with this prescription, they actually touch each other in this specific pattern here. Okay, so you get this fractal pattern. So this is interesting for us because, in fact, each of these circles here is a modular transform. So it can be mapped by a modular transformation to the circle, say, around 0. And circle around 0 is the one that we've already computed because it was giving us the major part of the amplitude. Okay, so the name of the game will be to deform the contour in such a way that it encloses these circles. And when that's true, then basically we can recycle the previous computation using modular transformations. Okay, so here comes the idea of the Rademacher contour, which is quite old. It dates back to the 1940s. And once again, we're going to label the contour f sub q, and we're going to follow all the 4 circles in a given Fourier sequence from 0 to 1/2. So this is much easier to draw than explain in words. So what we do here, gamma 2 means that we enumerate all the fractions with the denominator up to 2. So in that case, it's only 0 and 1/2. And then what we do is we start at 0, and then we follow the circle of 0 over 1 until the point where it touches the next one, which is the half. At that point, we turn back, and then we go follow it to the end. Okay, so this contour is actually precisely homologous to the contour that the gamma that I was describing before. It does something in the upper half plane, but ultimately it approaches 0 and 1/2 with the correct angle. And now what I'm going to do is I'm going to play a game, and I'm going to, this gamma is basically what we're interested in. And then the game that I'm going to follow is that we're going to iterate this, and then we're going to start enclosing more and more circles in the Fourier sequence. So for example, Fourier sequence 5 with these fractions in here. And then I'm going to follow 0, and then turn when I have 1/5 until I meet 1/4, 1/3, then 1/3 goes to 2/5, and then 2/5 meets 1/2 here, and then I close the contour. Okay, so it looks a bit crazy, but what I'm going to claim is that we're not done yet because we've not. I mentioned that circles are the ones that are nice computationally. But actually, this contour is none of the circles are closed yet. So what I'm going to do is something funny. I'm going to take the limit in which q goes to infinity. So that means that I'm going to consider every rational fraction, irreducible fraction between 0 and 1/2. And I'm going to enclose the corresponding circle exactly once. So as a result of that, I get this insane looking fractal contour. But the claim is that this contour is equivalent by contour deformation to the original contour that we're interested in. Okay, and now we can play the same game. We can shrink all of these circles to be arbitrarily small, and then basically we can compute all of them. So what I wanted to summarize here is that this gives us a representation of the one loop amplitude that is given as an infinite sum. The sum is over all rational points p over q, where for each of them I have to do an integral of the same type that we already know how to do, and it's a power series. So basically, the bottom line is that using this funny deformation, we managed to convert a complicated integral into an infinite sum. And in the infinite sum, the largest circles give us the largest contributions. So what this means is that we can, in principle, truncate the series at some large number, and this will give us a numerical approximation to the full answer.
Sorry, how did the 1 over q come? Is it easy to see why there's a 1 over q in this sum?
No, it's not that easy to see.
Okay.
So this comes from the you would have to study the integrand and look how exactly it looks like. Yeah.
Okay, thanks.
Okay, let me since this contour is slightly funny, let me kind of give you some intuition what these circles are supposed to mean. So each of them you're supposed to interpret as follows. So you're supposed to look in the case of the planar annulus and the Mobius strip. You can look what happens as you draw this unitarity cut and you look at the color line, so going between 1, 2, 3, 4, and then back to itself, how many times it crosses the cut. So we call it the winding number. So this one winds once across the cut, while for the Mobius strip, the color line actually goes twice. It goes 3, 4, then back to itself. So it goes back. If you try to track down what these modular transforms mean, then you can actually interpret them as these funny worldsheet geometries that wind around the cut exactly q times, where q was the denominator of the fraction. Okay, so that's kind of the geometric interpretation of the parts in the moduli space where they come from. But actually, we currently don't have a good physical interpretation of why. Is this just a mathematical trick, or is there maybe some deeper physical interpretation? That's an open question. Okay, but nevertheless, you can just, once again, you can put it on a computer, and then the result of this computation is basically this orange curve in here. Okay, so once again, you can see that the orange curve passes through all the integer points, so these dots, exactly. But we can also look how it looks like in between those points. So maybe one thing that I was supposed to mention before, but I forgot, was that there's actually a lot of results for the one loop amplitudes in the alpha prime limit. So this is roughly the limit in which the low energy limit, in which you can treat string amplitudes as an effective field theory with some alpha prime corrections. But unfortunately, we cannot exactly match on those results. And that's because these results break down at the first resonance. So the alpha prime expansion actually doesn't tell you much about these complicated curves. Okay, another thing that I wanted to emphasize is that if you actually try to count how many, for example, S equals around 15 or 16, how many two-particle states you have to sum, effectively you're summing over in the cuts, then the number of two-particle states is roughly 10 to the 15. That's because of the exponential degeneracy at higher and higher mass levels. So all these formulas is somehow summarizing all this complicated dynamics of these different excitation modes, and that's why you see these different wiggles. And once again, another thing that I emphasized before, but is much clearer here. If you compare the major part and the real part, the major part is leading by a couple of orders of magnitude. So that means that the string amplitudes at one loop are dominated by the on-shell particle production, or these thresholds. And let me also speculate that these wiggles, as I mentioned, they're essentially the effect of the complicated dynamics of the different excitation modes on the string worldsheet. So they're somehow encoding the chaotic dynamics of these modes, although how to make it concrete remains an open problem. Okay, maybe let me, before...
Sorry, Sebastian,
yes.
One question.
Mm-hmm.
In this alpha prime goes to 0 limit, you could have just plotted your formula for smaller values of S, right?
Yeah.
And then would it match?
So we actually did predict for the imaginary part, we did actually predict expansion in the alpha prime, which currently is the state of the art. So we definitely did match on the on the known results. However, specifically about this formula, let me mention that this formula, actually its convergence is good for large values of s, but as s goes to 0, it turns out that all these circles, they give you roughly a constant numbers.
I see.
And then we have a power series in 1/q. So that gives you a harmonic.
It's very slowly convergent or divergent.
It's actually very slowly divergent, and that's entirely expected. This is the sign of the fact that in the low energy expansion, we get log of alpha prime s. So this harmonic divergence is exactly the same phenomenon that we get logarithmic divergence. So that means that this formula specifically cannot be used to study very low S's. The divergence becomes worse and worse. But using similar techniques, we have a separate handle on these alpha prime expansions.
I see. And the log of alpha prime s is just from the QFT Feynman diagrams having some loop.
Yeah, exactly. Yeah, that's a super Yang-Mills or supergravity in the closed string sector.
Okay, thanks.
Sebastian, could you explain again why the discontinuities are barely visible? I think you mentioned this while discussing the imaginary part, but I missed it.
Why the discontinuities are so small, you mean?
Yeah.
So yeah, I'm afraid that once again, this is a computation. So basically you can, the computation would have to go back to these entirety cuts that I mentioned here. Basically, if you evaluate this formula on these circles, which I'm definitely not going to show on the slides because it's quite complicated, then you would see that new thresholds open up, and then you can study how fast they open up. And it turns out the result of this analysis is that they open up very slow. And I don't have a very good physical interpretation for that.
Okay, yeah.
The exception is the threshold at the 0 at the origin, which opens up as a log, as we said.
Right. Yeah. Okay, thank you.
Okay, great. So in the last part of the talk, so we talked a lot about the fixed scattering angle, and then what I wanted to mention is also some results about fixed momentum transfer, including some new results. So the fixed momentum transfer is also known as the Regge limit, and it turns out that using exactly the same technology, that all the contours and all that, we can actually, we can plug t to be, say, 0. So t equals 0 is the forward limit. And what I'm plotting here is, once again, in blue and orange, the imaginary and the real parts of the amplitude in the planar sector. Okay, so once again, we see here that the imaginary part, I even divided it by the factor of 20 so that it fits on the same plot, is leading by a large fraction over the real part. And the real part oscillates around the origin. Okay, we also have some preliminary results. So it turns out that everything that I said with the Rademacher contour can be generalized to closed string. There you have to be able to decompose the fundamental domain in terms of these circles and all that. And then here we have some preliminary results that are enough to plot the counterpart of all of this for the closed string. And there we also start, we've started to push the S to be higher and higher in order to be sensitive to high energy behavior. Okay, but one thing that I'm going to notice straight away is that let's focus on the open string. In the open string sector, the imaginary part goes roughly as a constant. And then it turns out that if you reinstate these prefactors, the T8 tensor that I mentioned at the beginning, that goes as S to this second power, so S squared. So that means that overall the amplitude goes like S to the second power. And that turns out to be somewhat of a a contradiction with the traditional law of Regge limit, which would tell you that the amplitude should go as to the spin of the exchange particle, which in that case would be 1. Okay, so basically it grows too fast. So let me illustrate this puzzle at the level of the cross section. So cross section that I'm plotting here. So this is the cross section for gluon going to anything at one loop. That is related to the imaginary part in the forward limit with a single power of s. So basically while the previous plot went to a constant, now it grows roughly linearly with s. So that's the black line. And what I've done here, just to illustrate this thresholds opening up and so on, I've actually split all the contributions into different masses of the mass levels of the states flowing through the entirety cut. Okay, so the blue is the massless. Then we have first level, 0, second level, and so on and so on. And as you can see, the threshold for example, the orange threshold opens up here. There's a discontinuity, but the effect of this discontinuity is not visible until somewhere here. Okay, so that's kind of.
Sorry, Sebastian, just a confusion about your previous comment about the spin of the exchange particle. Yeah. So the previous plot was for the annulus, right?
Yeah.
So at the annulus, this 2-to-2 scattering can exchange a graviton, right? Like in the closed string.
That's only in the non-planar sector.
Oh, that's only in the non-planar sector.
Yeah, yeah. Which you can also analyze, but I've not put it. It's in the papers, but I've not put it here. So yeah. Okay. So maybe at the level of the cross section, the puzzle is visible a little more because the cross section grows linearly, but a lot of considerations that relate to Regge limits and other things tell us that the cross section should actually saturate. So it should go to a constant. Okay. So now let's try to investigate this. Now that we have numerical data, we can actually compare different contributions. And it actually turns out that the dominant contributions come from this gamma. So from this CASP contribution. And the way to see it is that I mentioned already that limit is correct. You can evaluate it, and it turns out to be the alpha prime derivative of the Veneziano amplitude. So in equations, what I'm saying is that this dominant contribution looks basically like this, the Veneziano, and then you hit it with the alpha prime derivative. And if you do it, then you would find this expression that in the forward limit, t goes to 0, goes to a constant. Okay, so that constant was the leading piece that we've seen on the previous plot. But what's interesting about this is that, in principle, this kind of soft dilaton insertion is also going to happen at genus 2, genus 3, and so on. So let me explore a little bit this pattern at higher genus. So for example, at genus 2, we would have 4 surfaces contributing to the planar scattering. And the surfaces only differ by basically taking a small segment and twisting it a little bit. And we can do it in 4 different ways. So this is the analog of the annulus and the Mobius strip at genus 2. And basically what you can study is you can study exactly the same limit as we studied before, the one in which all the holes shrink to points. So basically they correspond to inserting a soft particle at these points. And then if you work out the details, it actually gives you not a first derivative, but instead a second derivative of the Veneziano amplitude. And as you might expect, this actually continues.
Sorry, Sebastian, I'm just being a bit slow. Is it easy to see why the alpha prime derivative brings down a soft dilaton? Just from the sigma model action, like usually the dilaton multiplies the G string in the action. Naively, an alpha prime derivative will bring down the entire world sheet action from the path integral.
Yeah, this is not, so more precisely, this is the log alpha prime derivative. I would have to think how how do you see it from the action? But yes, I think the intuition is supposed to be that it's basically a Lagrangian insertion of these things.
Okay. So I can think of it as some, okay.
Okay, so let me, thank you for the question. The pattern turns out to continue at higher genus, and basically the claim is that at every genus there's going to be a leading contribution, and that leading contribution comes from these degenerations, and each of them gives you an alpha prime derivative of the Veneziano amplitude. You can actually be careful about this. You can reinstate all the factors of G string and 4 pi and so on. This is the result. So as you might anticipate, what we're going to do now is we're going to resum this object here into an exponential. So that, strictly speaking, requires that S is large and this quantity is fixed. And what this looks like is it looks exactly now like a shift operator. It's a shift in the log of the alpha prime. So you can think of it as just taking the original Veneziano amplitude, and the result of this resummation is simply shifting the alpha prime and giving it a small phase. Okay, so if you do this computation, you just take the Veneziano amplitude, you do this shift, and then take T, the leading order in T. It actually gives you this answer in here. So that answer decays like 1 over S. And if you translate it back to the cross section, it was 1 additional power of S, so it goes to a constant. So you see that the effect of the resummation is precisely what restores the saturation of the cross section. So roughly speaking, what you would see here is that if you study it at every genus or every new genus, the cross section will grow as to the first power, to the second power, third power, and so on. But all of that, so you would see worse and worse, but all of that turns out to resum into a constant. Okay, and just as it's kind of one of the last slides, let me give you another interpretation of this result, which is the fact that I mentioned that the spectrum of superstring is quantized as integers over alpha prime. And now what we've done is we've added the small positive imaginary part to the alpha prime. Now it's in the denominator, so that means that the mass is squared. You get the negative imaginary part. So one way that you can think about it is that the effect of the resummation is that we had resonances on the real axis, but now the resonances move down into the imaginary axis, into the lower half plane, sorry, which is entirely consistent with the previous computations of the K-waves of these states. So if you wanted to study the physics, you would study it on the real axis, but the effect of the resummation is that everything else is moved away. And this actually pertains to the question of Ashok from a while ago, which said that equivalently we could have studied the same physics by basically doing not renormalizing anything, working at a fixed order in perturbation theory, but instead looking at the physics in the upper plane. And actually that slightly means that the G string is supposed to be, the angle at which you study it is supposed to be proportional to G string squared. Okay, so I'm basically done with everything here. Let me just mention that even though I went grossly over time with my talk, I've barely scratched the surface of the types of things that we can do. So in various different papers, we study different physical aspects that are now we can understand better using these numerical tools, including partial wave decomposition, including various different topologies and various planar orderings, closed string, open string, and all that. So you can find all these results in these papers. And with that, let me just move to the outline. Let me just give you the kind of broad summary. I motivated everything by the fact that we wanted to study better the high energy behavior of string theory in order to make contact with the string black hole transition. And then I mentioned specifically the one-sheet approach to this problem, in which there was a small puzzle about how to design the integration contour that was consistent with the principles of causality and unitarity. And then we resolved this problem by proposing a new integration contour, and that eventually allowed us to extract numerical data for the scattering at high energy in the fixed angle regime and the fixed momentum transfer. Okay, so with that, let me thank you for your attention.
Thanks a lot, Sebastian, for the nice talk. I have one question about this resummation that you mentioned. So typically when this Reggie amplitude grows too fast, like you had it growing like S squared, then people usually say that, oh, there's a higher spin exchanges that you have to resum, and that is the thing that softens the Reggie limit. Right, like a usual graviton exchange just gives S square, but then a resummation of the whole tower kind of reduces the power. Here, it's like a different effect.
Yeah, that's right. That's right. I agree. And
two related, or they are just completely different? What is the?
Yeah, I'm not entirely sure how they're related. One of the reasons is that it came from these kind of worksheets, and these do not look like. So these are roughly tadpoles from the QFT perspective, while what you were describing were like exchanges, say in the P channel. So it looks slightly different. And we're in fact trying to investigate what's the exact relationship between the two types of analysis.
Because you already have an S to the alpha prime T minus 1 overall, right? Could you go back to this?
Oh, yes, sorry.
No, that formula.
Yeah.
Right, so there's an S to the alpha prime T, but in the 2 slides later, you also had a S to the alpha prime T minus 1 here.
Yeah. So that thing is the effect of the resummation. So this basically brings everything down to the tree level.
I see.
This is the tree level growth.
That you have stripped out the polarization factor, right?
Yes, exactly. Sorry. So there should be the T8 tensor that grows as 2 powers. So the overall, if you reinstate those powers, it will be S to the first power, which is exactly what you expect.
I see. So somehow this, I see. So the tree level is okay. The tree level would just give you exactly this power. And somehow the resummation of these soft dilaton insertions is, as you said, bringing everything down to the tree level power of S to the alpha prime T. Okay, interesting. And then the cross section, you said, sorry, one more time. The cross section, you just add one more power of S to this formula, not to the T8. Okay, I see.
Yeah.
I see.
Exactly. So you would really multiply it by T8 divided by S. T8 grows as S squared divided by S. So that's 1 extra power.
Okay, thanks. Do you have any?
Yeah, thank you for questions.
Yeah. Are there any questions on the Zoom if people are still there? Okay, looks like not. Okay. Thanks, Sebastian, for the very nice talk. Yeah,
thank you so much for the invitation and for all the questions.
Hope to see you in person sometime soon.
Likewise.
Bye.
All right, bye.